So you're going to look at 8.5 part 3, which is what's called the dot product. Has anybody done dot products before? Okay, so I told you we talk about how to multiply two vectors together, and this is one way that you can do it. When you talk about multiplying vectors, you generally can't just say take vector v and multiply by vector w. Multiply is, it's not specific enough. When you multiply vectors, there are, especially in 3D, there are two ways to do it. In 2D, there is only one way. So if you're doing vectors in 2D, somebody would know what you're talking about. But in 3D, you can do what's called a dot product, or you can do what's called a cross product. And they're completely different. Okay. So let's say we have these two vectors. They're two-dimensional. They have a horizontal and a vertical component. The horizontal components are A1 and A2, and the verticals are B1 and B2. Those would all be numbers. Okay, so when you're doing an actual problem, you'll have something like, well, I'll do one with numbers after, but you'll have all numbers in those four spots. Okay, the way that you find the dot product is you're going to use those four, they're like coefficients, right? The four things in front of the i's and j's. And to find the dot product, you do A1 times A2, that's the horizontal components. You do B1 times B2, that's the vertical components. And then you add the result. So based on doing this calculation right there, what kind of answer do you think you're going to get when you do v dot w? Yeah?
The vector.
No, we're not going to get a vector.
Oh, yeah.
Yeah? A number, yes. We're doing a number times a number. We're doing another number times a number. And a number times a number is a number. And then we're adding a number to another number. So adding numbers to numbers, you get numbers. So the dot product is a number, like 7 or -2. It's a number. Okay, so we'll practice finding a dot product, and then I'm going to show you what we use it for. Okay, so here's two vectors, 2i minus 3j, and 5i plus 3j. And the way you pronounce what they want you to find here is v dot w. That's how you say it. We're going to find v dot w. Then we'll do w dot v. See what happens. Okay, so to find v dot w, that's going to be your calculation you're going to set up. And what's going to go in the first two parentheses?
2i.
Yep.
2 and 5.
2 and 5. So 2 times 5. And what's going to go in the last two? Yeah. -3 and 3. And it should be in that order because you're doing v dot w. So the v comes first, w comes second. V, then w. Okay. And if we do that out, what do we get for a final answer? Yep.
1.
1. So the dot product of v and w is 1. Okay, let's try it the other way. Let's try w dot v. What's going to go in the first two parentheses this time? What times what? Yep.
Would it be 5 times 2?
Now it would be 5 times 2.
And then
So
3
5, 2, and then
times -3.
3 times -3. And what's the dot product this time?
1.
1 again. Doesn't prove something, but it suggests that the dot product is what? Yeah?
Commutative?
Commutative, and it is. It is commutative. So when you are doing dot product, you can switch the order and you get the same answer. All right. So now let's try v dot v. Okay. What would be my calculation for v dot v? Yep. Holly?
2 times 2 plus negative 3 times negative 3.
2 times 2 plus negative 3 times negative 3. You're dotting a vector with itself. 2 times 2, and then negative 3 times negative 3. Okay. What would that come out to for the dot product? Yep. 13. 4 plus 9 gives me 13. What's another way of saying 2 times 2? Yep.
2 squared.
2 squared. And what's another way of saying negative, well, negative 3 times negative 3? Yeah?
Negative 3 squared.
Negative 3 squared. So look at what we just did. We squared that number, we squared that number, and then we added them together. That's kind of like doing something we've done before. Not exactly, but it's close. What is that kind of like doing? Yeah? Kind of like doing Pythagorean theorem, but what didn't we do? Yeah?
We did not square root our answer.
Right, we didn't take the square root at the end. Okay, if you were going to find the magnitude of v, and this is important, the magnitude of v would be 2 squared plus negative 3 squared, but then you would square root it.
Square root.
So the magnitude of v is the square root of 13. What we did, we got 13. We didn't get the square root of 13. So dotting a vector with itself really gives you what? Yeah?
Magnitude squared.
Yes, that's very important. Dotting a vector with itself is close to doing the magnitude, but you don't take the square root. Okay, so dotting a vector with itself gives you the magnitude of the vector squared. 13, the magnitude is the square root of 13. Okay. Any question on that idea? We're going to need that formula later on. And that would work for W. I'm not going to do W, but if I did W dot W, I would get 5 squared plus 3 squared. Okay, and we just wrote that down. So when you dot a vector with itself, you get the magnitude squared. Okay, so now let's look at this one. The vector 2, 6 dotted with the vector 0, 0. What are we going to get when we do the dot product between those two vectors? Yep.
0.
0. 0 the number or 0 the vector?
0 the number.
0 the number, yes. Not a bold 0. Not a 0 with a line on top. When you do a dot product, the answer is always a number, okay, not a vector. And that means something. When the vector has a dot product of 0, we'll talk about that. All right, so when you are doing multiplication, I showed you an example where we switched the order and we got the same thing. It means it's commutative. You can't assume that any other properties you know about regular addition, subtraction, multiplication, division, You can't assume any of those work with vectors. Okay. With dot product, a lot of them do. With cross product, one that doesn't work is commutative. Okay, when we do a cross product, which we'll do tomorrow, if you switch the order you multiply in, you don't get the same answer. So that's very different than what you're used to. But dot product, it is distributive. So you could do FOIL with it. You can, double distributive property. This is just a single distributive property. But you could do U dot V plus U dot W. Or you could add V and W together first and then do the dot product second. So you can distribute if you want. That does work. Okay, and we're going to need that idea for something we're going to do in a minute. All right, so what do we use the dot product for? Well, dot product is going to be important when we're trying to figure out the angle between two vectors. There's two vectors, and when I say the angle between them, I mean that angle right there. It's the angle inside the vectors. It's always less than 180. If you wanted the angle on the outside of the vectors, well, you just get the one on the inside and then subtract it from 360. All right, so I want to find that angle. U and V, those are bold, those are vectors. And anybody have an idea of what shape we are going to make to figure out that angle? Yeah?
Triangle.
Yeah, we're going to make this into a triangle. What we need to do is figure out the third side. Well, the third side is a combination of these two vectors somehow. Does anyone see how I could combine these two vectors together and it would give me the third side? So we don't need a new name for it like W. It's the third side. You can combine U and V the right way, and it will automatically give you a side that looks kind of like that. Yeah.
Did you add or would you subtract U from V or V from U?
Okay. Tell me what to write down. Give me exactly what you're thinking.
I think it could either be. Oh wait, no, it's U minus V.
Yeah. It's U minus V. That's what that third side is. If you don't see it, well, take U. I'm just going to draw it. And then reverse V, like that. Okay, that's the negative of V. Put that on the end of what we've got right there. Now, connect where you started to where you stopped. That'll represent U minus V. Like that. Now drag that over and see if it lines up with the vector I just drew. Yep, that's U minus V. Okay, so that third side is U minus V. Any question on that? All right, now, we've got a triangle here. I want to figure out this angle. Well, based on what I have on that board, what could I figure out in that triangle right now? If I wanted to. Especially because there's a grid behind it. Yeah?
Distance of each side.
Yeah, I could find the distance of each side. Yeah, it's just the Pythagorean theorem 3 times, but I could do that. And then if I knew the distance of each side, what kind of triangle would that be? A lot of times we describe it with like 3 letters. Yeah?
Side, side, side.
This would be a side, side, side triangle. how do you find out angles in a side-side-side triangle? Yep.
Law of cosines.
Law of cosines, yep. So we need to do the law of cosines. Now, when you deal with law of cosines, the formula has a spot to plug in an angle, and it also has spots to plug in what else? Yep.
Side lengths.
Side lengths. Okay. We have vectors here. How are we going to represent lengths of these vectors? Not the vector itself, but the length of the vector. Yep.
The magnitude of each one.
The magnitudes, yep. So we're going to have to put double bars around everything to indicate we're dealing with the length of the vector, not the actual object that is the vector. Okay, we want the length of it. So remember, law of cosines follows a pattern like this. We just have to fill that all in. So you always start with the side that's across from the angle you're trying to figure out. That's going to be u minus v. Because I want to know that angle right there. So we've got magnitude of u minus v squared equals what would be in the next box? Yep. Could be more specific. I need a little bit more information. Like just like that.
I mean, you have the v squared with bars.
So magnitude of v squared. Yep. And then the next one would be, yep,
Magnitude of u squared.
magnitude of u squared minus 2, and then it's what comes in these two boxes. Yep.
2u.
Magnitude v, magnitude u, cosine theta. There's our formula. So that's law of cosines, just filling in our three sides of this diagram. Okay. Any question on that? All right, I don't see any dot products here, but there's going to be. The magnitude of a vector squared. We talked about that earlier. Instead of writing the magnitude of a vector squared, you can write it as the dot product with itself. So how could we write magnitude of u minus v squared? Yep.
U minus v times u minus v.
U minus v dot u minus v. And we know distributive property works because I told you that. So we're going to come back to that in a minute. But let's do that for all of them. How about magnitude of v squared? How could you rewrite that one? Yep.
V dot v.
V dot v. And how about the magnitude of u squared? Yep.
U dot u.
U dot u. The rest of that we can't really do anything with, and all of that's going to end up in the final answer. So 2 magnitude v, magnitude u, cosine theta. All right, let's do out the left-hand side. That's about all we can do right now. All right, so we got u dot u. We've got u dot negative v, and then another u dot negative v. So how many of those u dot negative v's do we have? Yep.
2.
2. And they're negative. So negative u dot v, negative u dot v, that's negative 2 u dot v. And negative v dot negative v. Negative times negative is a positive. So negative v dot negative v is really positive v dot v. And now copy down the rest of it. V dot v, u dot u, 2, magnitude, magnitude, cosine. Now, what's going to happen if you look at what's on the left and the right in the next step? Yep.
You can take out a few things, like you can divide u dot u from both sides. Take
So
out
you can, you can't divide it from both sides. Can't do that. Yep. You can subtract it from both sides, yep. All right, anything else? Yep.
You can subtract v dot v from both sides.
Subtract v dot v from both sides. All right. I guess let's write down what we have now. We can look at it again. So we have negative 2 u dot v. All right, that's gone, that's gone, that's gone. And then we have equals negative 2 magnitude v, magnitude u, cosine theta. All right. What could we do now? Yep.
divide both sides by -2.
Yeah, we can cross out that -2 from both sides. And then they usually write the formula with cosine theta alone. What would be in this box if you put the cosine by itself? Yeah.
U dot v divided by magnitude v magnitude u.
Yeah. So very nice, compact little formula to find the angle between two vectors. It's the dot product of the vectors divided by the product of the magnitudes. And that's equal to the cosine. Okay, you could take the inverse cosine on each side and write it that way, but that's how it looks in our book. So it's the dot product over the product of the magnitudes. So that is really doing the law of cosines for you. And a lot of things end up canceling out, which is why the formula gets quite a bit more compact than what you had up at the top. Okay. So it's all based on a side-side-side triangle. So that's what we just wrote down. So to find the angle between two vectors, the cosine of the angle is the dot product over the product of the magnitudes. Remember, magnitude just means length. So the denominator is the length of u times the length of v. So there's three things you have to find when you want to do an angle. You need a magnitude, and a dot product. You got to do all three. Unless it's a special case, then you might have a shortcut and not have to do all three. But we'll see. So let's look at these two vectors and find the dot product. Find the angle. So a question like this in the homework, they may give it to you in 3 parts. They may say find the dot product in part A, find the magnitude of u and the magnitude of v in part B, and then find the angle in part C. Well, they're all related. You got to do one to do the other anyway. So, all right, let's start with our dot product. Okay, first two numbers that I'm going to multiply to get my dot product are what and what? Wait.
4 times -3.
No, not 4 times -3. 4 times 2, yeah, which gives me 8. And then the next two would be, Jack, next two.
-3 times 5.
Yep, which is how much?
-15.
-15. And 8 minus 15 gives me -7. Yep. Okay, so there's my dot product. Now we need the magnitude of u. It's going to be the square root of what squared plus what squared. Nick?
4 squared and negative 3 squared.
4 squared, negative 3 squared. Yep. So the magnitude of u would be how much?
Be square root of 25.
Yep, which is 5. Okay, so we got the magnitude of u. Last thing we need is the magnitude of v. How about Dex? What's going to be the formula for magnitude of v?
It's going to be 2 squared plus 5 squared.
So 4 plus 25. And that gives me square root 29. Now, fill those three things into the formula. Okay, cosine theta equals, what's going to go on the top? Yep,
Negative 7.
the dot product, negative 7. And what's going to go on the bottom? Quick.
Square root 29 times 5.
Yeah, and I'm just going to put the 5 in front. That way there's no confusion whether that 5 is under the root or not. Okay, so 5 root 29. So that's the cosine of your angle. Now, how would you actually get the angle? Not cosine of the angle. Yep.
I take the inverse cosine on both sides.
Take the inverse cosine. So inverse cosine of negative 7 divided by 5 root 29. That gives you an angle of, I just must have typed something wrong. Inverse cosine of negative 7, okay. I didn't type anything numerically wrong, but I didn't put parentheses in the right spot. Because that denominator has a product in it, you need to put that product in parentheses, or it's going to do negative 7 divided by 5 first, and then multiply that by the square root of 29, and that's not exactly what I want. I want 5 root 29 all in the bottom, and now that works fine. So that's an important thing to remember. Okay, 105.0, we'll call it 07. And that's the angle between the two vectors. Right. Any question on that? So do you need that formula to do it? No. You could draw a triangle every time and go back to using the distance formula, Pythagorean theorem, 3 times. And then you could draw a triangle with those 3 side lengths and do law of cosines and get the angle. But it's going to be a lot more work than just using that formula. All right, so 2 special cases you can have for vectors are what we call orthogonal, which means they are perpendicular. Just when they talk about vectors, that's the word they use. So if they are orthogonal, which means perpendicular, it means the angle between them would be what? Yep.
90.
90 degrees. Yep. So think about what would happen if the angle between them was 90 degrees. You would have, like when you're doing the problem out, you would have a dot product. You'd have the product of the magnitudes in the bottom. And let's say we knew ahead of time, somehow, that the angle was 90 degrees. I don't know what the dot product or the magnitudes are going to be. They're numbers. Okay? But the angle is 90 degrees. If you fill in a 90-degree angle on the right side, what's the cosine of 90? Think of the x value of the coordinate for 90 degrees. Yep.
0.
0. So if you end up with a situation where the vectors are orthogonal, you're going to end up with a 0 on the right side. That's going to equal something on the left. What's the only way that a fraction can ever come out to 0? There's only one way. Yeah? If 0 is in the numerator. What is in our numerator on the left-hand side in general? It's the what? Think about when you're finding an angle, what's in the top? Yeah?
U dot V, or
Yeah.
vector dot vector.
Yeah, the dot product. So the only way that two vectors can come out to be perpendicular is if the top of this fraction is 0. The only way the top of that fraction can be 0 is if the dot product is 0. So there is a shortcut to figure out if two vectors are perpendicular. If their dot product comes out to 0, you're done. They are perpendicular. Because that would make the top of this 0, which would make this side 0, which means you must have an angle of 90 degrees. Now, you might think, well, wait, there's another coordinate on the unit circle with that has an x value of 0, 270. But we're always talking about the angle between the vectors right here. We're not talking about the angle outside there. So. All right, so let's look at this one. And the question is just, are these vectors perpendicular? Doesn't say if they're not, find the angle. It just says, are they perpendicular? So that's a pretty quick problem. What's going to be the dot product between V and W in this case? Oh, Cecilia, what's my dot product here? Four. What is the dot product supposed to come out to if they're perpendicular?
0.
0. So are these vectors perpendicular?
No.
No. Because you have a 4 in the top. There's no way with a 4 in the top you would ever get this fraction to equal 0, which means there's no way this could ever be a 90-degree angle. So the answer is no. Okay, so perpendicular, that's one special case. Anybody have a guess what the other special case is between two vectors? No?
180, or would they
What would you call that?
parallel?
Parallel. There's actually two ways vectors can be parallel.
Mhm.
You could have vectors like that, or you could have vectors like this. In the second case, the angle between them is 180. In the first case, the angle between them is 0 degrees. Mr. Hager? Okay, so yeah, the angle is either 0 or 180. Let's think about what would happen if the angle was 180. You'd have a 180 on the right side, and that would be equal to a dot product over the product of the magnitudes. What's the cosine of 180? Yep.
Negative 1.
-1. So it's not a 0 this time. But what would happen in a fraction for it to equal -1? What has to happen in a fraction for it to come out to -1? Yeah.
It has to be the exact same as in the bottom, but negative.
Yeah, so you're dividing opposites. The problem with that is, to know if you have opposites in a fraction, you need to not only know the top number, you do have to know the bottom number. So when you are finding if they're parallel, there's no way around having to figure out the top and the bottom. Now, the other case that you could happen, instead of them being 180, the angle could be 0. Think of the vectors as being like right on top of each other. I just drew them separate so you could see. If the angle between them is 0, you'd have 0 degrees in parentheses there. What's the cosine of 0? Yeah?
Positive 1.
+1. What's the only way that a fraction can come out to +1? Cool.
Both the top and bottom are the exact same.
If both the top and the bottom are the same. Unfortunately, the only way if you know the top and the bottom are the same is if you know the top and the bottom. So you have to find both. All right, so let's try this one. Determine if V and W are parallel. So let's do the dot product. What's 4 times 20? Yep. 80. What's negative 5 times negative 25? Yeah.
125.
125. Add those up. We get a dot product of 205. Magnitude of V. 4 squared plus negative 5 squared. As an exact answer, what does that give me for the magnitude of V? Yeah. Yeah, go ahead.
I don't know if you said exact, just got decimal, but for decimal it's 6.4031.
Yeah, we want to keep it exact. We don't want to do any rounding. So what would that be?
I was just 41.
Yeah, just a square root of 41. Okay, and this one, 20 squared, how much is that? 20 squared is
400.
400. Negative 25 squared, what's 25 times 25?
625.
625. So that gives me the square root of 1025. All right. I don't really care about doing inverse cosine. If all I want to do is determine parallel or not, just see if the top and the bottom comes out the same. Well, the top is 205. The bottom is the square root of 41 times the square root of 1025. Let's type it again. It's rough. Square root of 41 times the square root of 1025. I got 205. What did I have in the top? 205. So because you have 205 in the top and 205 in the bottom, you would be setting up something like this. Dot product over the product of the magnitudes equals cosine theta. That's 1 equals cosine theta. If you take the inverse cosine of 1, you will get one of the angles that indicates they are parallel. In this case, the angle between them is 0. So these are two vectors pointing in exactly the same direction. They don't have to be the same length. Okay, parallel vectors are not the same length, and you can see them. The lengths are totally different. W is a lot bigger than V. But they're doing something like this. That's basically what they look like. All right, any question on that? All right, so last question. Oops. So the last question is going to be about an airplane. First, one thing that's important to understand about airplane is the difference between ground speed and air speed. Okay. They're not the same necessarily. Ground speed would be like if you were on the ground and you could point a radar gun at a plane and see how fast, or if you were like up at the same level as the plane and you point a radar gun at it and you see how fast it's moving. Okay, that's like the ground speed. The air speed is like if you put your hand out the window, how fast the air is hitting your hand. Well, you might think, aren't they the same? No, they're not always the same. If you were driving at 50 miles an hour and there was no wind, and you put your hand out the window, then the speed on your car would say 50, and the speed of the air hitting your hand would be 50. But let's say that you are driving into a 20-mile-per-hour wind coming right at the car, and your speedometer says 50, but you put your hand out the window. How fast is it going to feel like the air is hitting your hand?
70?
70, because the air is moving at 20. The car's not going 70. The car speedometer says 50, but the wind is blowing at you at 20. So that's the difference between the airspeed and like your speedometer speed. Okay. So that's going to come up in this problem. Yep.
So would that mean a tailwind, just like the wind coming from the back blows them forwards? Would
Yeah.
mean that, say if it's an air, like a movement speed of like 500 and a tailwind, you know, maybe 800, you'd be like 420 for airspeed? Because it was track.
Yeah, it could. Yeah, I would subtract. It would slow it down. Yeah. And that's why if there's not enough air moving over the wing, you reach what's called the stall speed. Stall speed is bad. If you don't have enough air moving over the wing, there's not enough lift to keep it afloat. Or, yeah, afloat in the wind. All right, so our particular plane is maintaining an airspeed of 500 miles per hour south, and there is a jet stream 80 miles per hour northeast. There's a couple ways they can describe the direction of the wind. They can describe it like I did here and just say that the jet stream is blowing in a northeasterly direction. Or they can say the wind, the jet stream is coming from the southwest. So you have to be careful how they phrase it. A wind coming from the southwest is blowing towards the northeast. Right, so if you hear the weather, like they say the winds are out of the west this afternoon, that means they're blowing to the east, from the west to the east. But this one states it pretty clearly. The jet stream is blowing in a northeast direction. It says to find the actual speed and direction of the aircraft relative to the ground. We're going to just probably do the speed. We're not going to do the direction. Okay, the direction would involve finding an angle. All right, a lot of words. What do you think we should do with all that? Yep.
We've got the valuable information.
Okay, and what we're going to create something.
Okay.
What are we going to create? Yep. We're going to create equations. That's going to be secondary, though. First, we need to create something else to help us get equations. Yeah?
A data table of like, say, airspeed 500 miles an hour, jet stream 80 miles per hour, and just get
Okay, you could make a table. I'm not going to make a table, but you could. Yep.
Picture?
Yeah, you need an image of all this, right? And we need to convert everything into vectors, right? Specifically velocity vectors. So it says the airspeed of the plane is 500 miles per hour south. All right, so let's start with that. Let's draw a velocity vector for the airplane going 500 miles per hour south. I'm going to call that v sub p. That's the velocity vector for the plane. Now it says the jet stream is blowing in which direction? Yep.
80 miles northeast, or mile per hour northeast.
It's blowing northeast. That's east. That's north. It's northeast is exactly between the two. Okay, the angle, I'm going to make the angle of the jet stream pretty easy to figure out. Right? It's not going to be anything complicated. It's either going to be northeast, southwest, or a combination of the two. So this one is blowing northeast. Right? Now, if you put that on the end of the plane, and let's label that. We'll call that, I don't know what you want to call it, velocity of the wind, velocity of the jet stream, just something you can remember. We'll call it velocity of the wind. It's going to blow the plane off course a little bit. Right? The actual vector for the plane is going to be that. So the velocity is going to slow the plane down because it's blowing north and east. And it's going to blow it a little bit off course. The amount off course, that's the angle that they're asking about in the problem. So I'm going to call that the actual velocity vector for the plane. Okay. Let's start with describing the velocity v sub p. We need to write a velocity vector. If you were going to write this with ij notation, it only has one component. Does v sub p have an I component or a j component? Which one? Yeah.
No.
Yeah.
J.
Just a j. And specifically, a negative j. If you want to be even more specific, it's negative 500j. That's the velocity vector for the plane. There's no, there's nothing else. There's no I component because v sub p is south. All right. Now, the velocity vector for the wind, that's a little bit more complicated because the velocity of the wind is at an angle. What's the angle of the wind? And if you get stuck, you can kind of think of it as being like right there. It's not north, it's not east, it's right in between the two. So what's the angle of the wind? Yeah,
45 degrees.
45 degrees. And what's the magnitude of the wind? Yeah, 80. You need to break the wind up into its components, the horizontal and the vertical. So think about making a triangle. Okay, so the horizontal component is magnitude of the wind times the cosine of the angle plus magnitude of the wind times the sine of the angle. And we would do that out, which I'm not going to do right now. The last vector we need is the actual vector. The actual vector is a combination of the plane and the wind together, specifically adding them together. That's what that visual is right there. So v sub a is the other two added together. V sub p plus v sub w. Once you do this out, you'll be able to add the two together by combining like terms. And then you'll have a vector that represents the actual direction of the plane. So we can finish that one up tomorrow. Okay, so the homework is 7 to 17 and 25. 7 through 17, it has 3 parts. I think it says find the dot product, find the magnitude, then find the angle. So they're all connected. And 25 is an airplane problem, which we'll probably want to do in class tomorrow.